I welcome you all to my video lecture series on graphene and amazing nanomaterial. Today's lecture is actually in continuation of my previous lecture number 2, where I talked about the types of nanomaterials and quantum confinement. Just for recapitulation, let me say a few words about that. We discussed what are the different types of nanomaterials. I mean, 0-dimensional, 1-dimensional, 2-dimensional, and the bulk material is 3-dimensional. In 1-dimensional nanomaterial, the carriers are free to move in one direction. That is why it is named as 1-dimensional nanomaterial. In 2D nanomaterial, the carriers are free to move in 2 dimensions. That means on a plane sheet. And in 0 nanomaterial, there is no free movement in any direction. All the directions of motion are blocked. In this way, we discussed in my previous lecture the different types of nanomaterials and the related confinement, the physics of the quantum confinement of the particles in the material. And also, I discussed some prerequisites on quantum mechanics because I felt that it is really necessary to have a basic knowledge about this quantum mechanics in order to understand the physics of nanoscience and nanotechnology, where I try to give you some idea on what we mean by matter wave, then some fundamental relations like the Broglie relation, Planck relation, and also I discussed the Schrödinger equation of motion, and a few words about where quantum mechanics is to be applied. It is very effective, not the classical mechanics. Today, with this recapitulation of the previous study, my lecture will cover today mainly the structuring of energy levels. What I mean by structuring of energy levels. See, to deal with the motion of the carriers in nanomaterial, we took help of Schrödinger equation. In my previous lecture, the Schrödinger equation, we solved the Schrödinger equation of motion of the particles in nanomaterial. The Schrödinger equation was written like this. D square psi dx square plus 2m over h cross square E minus v psi equal to 0. Also, I talked about what we mean by these symbols. M is a mass of the carriers. If we take electron as the carrier, then m is the mass of the carrier, and it is actually the effective mass. So, in order to let you understand effective mass, I am giving a star symbol, 2m star, where m star is the effective mass of electron. If you take the holes, then effective mass of the holes, it is effective mass. E is the total energy, V is the potential. Now if in a material, I am taking a material, if it is free in all the directions, the x direction, y direction and z direction, then the potential energy may be taken as a reference as 0. It is under no force field, that is why it is called free. So if we consider electrons only, then the electrons are moving in the force free field. The potential energy as a reference, I am taking 0 value. So this gives rise to d square psi dx square plus 2m star over h cross square E psi equal to 0, where the energy E, this is equal to p square by 2m star, where p is a momentum. Now quantum mechanically this is equal to h cross square k square over 2m star, where k is the wave vector, magnitude of the wave vector is the wave number, k equal to 2 pi over lambda. K vector, take the modulus, it is 2 pi over lambda. Now if it is free to move in all directions, in Cartesian coordinates, x direction, y direction, z direction, I am taking this x, y and z direction, it is moving in any direction. That means it can be resolved into x part, y part, z part. In this case, when the particle is freely moving in all the directions, then the wave vector value can take any value which is continuously varying. I mean, the set of values k, this is a continuum. What I mean by continuum means the k value, the wave vector value may take any value continuously, not selected values, that we proved in my previous lecture. But when one direction it is blocked, is gradually becoming scaled, say this is, for example, energy, this E equal to becomes h cross square over 2m star, k square, you just break it into 3 parts, kx square plus ky square plus kz square. What I told that kx, ky, kz, they may take any continuous value, continuous values. It is a set of continuum set. But if supposing this z axis, this is gradually shrinking like this, right? So it is a scale down and down going to the nanometric size. Then what happens? This kz, the movement of the electron in the z direction is confined. It is not free. So the electrons, they are now free, not in the z direction, they are confined in the z direction, but it can move freely in the x direction and y direction in the plate, in the plane movement. So this is actually kx, ky, these are free. I mean, they can take continuous values, but it is restricted. Kz becomes restricted, and we notice that what is that restriction? It is n pi over L, where n is a number which runs from 1 and so on, and L this is the dimension in the z direction. Dimension in the z direction. That means that it looks like this is extremely small. This value is extremely small. We dealt in my previous lecture as if there is a potential barrier in the z direction, both up and down. So the electrons cannot penetrate the potential barrier. We assumed the electrons cannot move and cross the potential barrier. So its motion is restricted. But it can move freely. There is no potential barrier. So the restricted motion is in the z direction, and the k value takes only some chosen values. 1 pi by L, L is this, z equal to L, I mean this. One potential barrier is here and another potential barrier is here, up and down. The two potential barriers are there, and these two potential barriers makes a well. So it makes a well, I mean that it can move only, suppose it can move only in this x and y, but there is a potential barrier like this. It cannot go this side, it cannot come to this side, but it can move here, you see. So this is actually the physical picture of the confinement of the electrons within this plane, and this is the potential well. Okay, so what is the energy? The energy now becomes E equal to H cross square 2m star kx square plus ky square plus h cross square 2m star into n pi by L whole square, where L is the dimension in the confinement direction, dimension of the nanomaterial. Now obviously you notice that the energy, the total energy, this is the total energy, and this total energy is sum of the two terms. One is this term and another is this term. Now this is actually the kinetic energy of the particle. And what is this? This is the energy which is a quantized energy. I mean the total energy was this, kx square, ky square, kz square. Look here, kx square, ky square. This kz changes to this value, and this value is a constant value. For n equal to 1, one constant, for n equal to 2, another constant comes on. This energy, obviously, as there is no k as such, it is not the momentum. It is not the, there is no k here. K gets a fixed value. Now this fixed energy, this is actually the potential energy. So it is interesting to note that the energy, total energy of the electron in the nanomaterial is now divided into two. One is the kinetic energy part and another is the potential energy part. Now you notice that when it was free to move in all the directions, there was no potential energy. I started from there. Now you see there is a potential energy. I am not giving any force from outside. Simply by scaling down one direction, the potential energy comes up. And where from this potential energy comes up? You know that according to conservation of energy principle, You cannot create energy out of nothing. So here, out of this total energy, a part of the energy is transformed into potential and the rest part is kinetic. So the energy, I should say that the energy spectrum I mean E and K, E versus K, this E versus K spectrum, it changes. Here the spectrum looks like this, continuum spectrum. Here you see some part becomes discretized, digitized, fixed values. So this a packet of energy, another packet of energy plus free energy. This is the bound energy. The potential energy is bound energy. Okay. So the energy, therefore, it is restructured. Restructured of the energy means how the energy levels are structured in 3 dimension, in which the electrons are moving in all the directions. There is some structuring of the energy levels, but when one dimension is scaled down, then the some part goes to potential, some part kinetic, so energy is restructured. The energy levels are restructured. Similarly, in the case of other, say I am now just scaling down not only z but also y direction. So this is a scale down and this is also scaled down. So it becomes like a wire in the x wire. So here again the another part will be quantized. I will go to that next time. But the point is this, that as it is a scale down in different dimensions, then in those dimensions the corresponding energy levels, they are restructured. So if we believe the restructuring of energy levels when the material is gradually shrinking in size, obviously those levels of energy, how those levels of energy are spaced in between the two levels. What is the distance of separation, energy distance of separation between the two levels? That may change, that will change. That is a restructuring. So the number of energy levels within some energy interval, how many levels will be there, that will change due to this restructuring, and that is the meaning of restructuring. Now with this idea, we shall define another quantity which is very important in order to understand the transport, I mean the voltage current relation in nanomaterial, that is your density of states. So the term density of states is important, and it comes because of the restructuring of the energy levels. Now let me see what I mean by properly the density of states. Okay. Now first of all, let me define what I mean by density of states. See, two words, one is the states and another is the density. Now what do you mean by the states? The states is the thermodynamic state. The thermodynamic state means It is given by different parameters like pressure, volume, temperature, energy, momentum, say I am giving small p momentum, like this. These are all thermodynamic coordinates, and this will give the physical condition of the system, the electron system in the material. I mean, suppose I am taking a metal or a semiconductor. There are so many electrons. What is the total volume, the space occupied by all these electrons, the particles? What is the momentum of individual particle, or the average momentum? What is the total energy of the electrons inside the system? This gives the states of the system, electron system. So the states may be labeled by energy, the states may be labeled by momentum at temperature, and so on and so forth. So I will take interest on the energy state or the momentum state. So now we understand what I mean by the state of the system, the momentum state, the momentum condition, that means, of the electron system or the whole system. Whole means HOLE, whole, the carrier. What is the energy of this electron system in a semiconductor or metal? So these are the states, state values. Well, now suppose, for example, I am taking the energy state. Now let us come to the definition of the density. In our school, that we know that density is this mass density. What is mass density? It is a state density. Mass density, mass per unit volume. Similarly, here it is a states per unit volume. States per unit volume of the specimen. So I am taking, suppose this is my nanomaterial. So how many energy states you can say, or if you take momentum state, how many momentum states in unit volume of this specimen, unit physical volume of this specimen. But this is not the complete definition of the density of states. To complete the definition of the density of states, I must say not only in unit volume, but also you count those states within unit energy interval. Suppose I am taking, say, energy, suppose 2 milli electron volt and another is 3 milli electron volt. See, count 1, 2, 3, 4 like that, you count. So counted values of the energy levels within this unit distance of separation of the energy in unit volume of the specimen. Let me repeat this. It is a number of states per unit energy interval per unit physical volume of the specimen. Okay. Now this density of states, say I am just giving the abbreviated form DOS, density of states. The definition is like this. Now we should be careful at this point. If we count from 2 MeV to 3 MeV, unit energy difference. But if we count from 3 to 4, will the two counts be same? If it is say 10, for example, not at all 10, huge and huge value. If it is 10, it may be 12, it may be 100, it will change. Then the density of states, therefore, the number of states, if you count from 3 to 4 for the same material and unit volume, it is differing if you measure from 2 to 3. So, density of states is not a fixed value, it depends from which reference energy value you are counting. So, the density of states actually is the function of energy. If you count from 2 MeV to 3, density of states is something. If you count from 3 to 4, something. So, density of states D, I mean DOS, I am abbreviating D, it is a function of energy, dE. So, this density of states is a function of energy. So, we noticed that what exactly we mean by density of states and what is the importance to understand the density of states. It gives us the idea of how to calculate the total number of electrons in a system. In order to understand the number of electrons in a system, the density of states, that should be known beforehand. And at the same time, I already told you that the density of states is very much essential to understand how the energy levels are restructured, right. So, now let me see the density of states due to the restructuring of the energy levels, how they change from 0 dimension to 1 dimension, 1 dimension to 2 dimension, and so on. Let me start from the bulk material. In the bulk material, I am taking say (3D) material. The density of states if we give this density of states in the x-axis, energy in the y-axis. Because you know that the density depends on energy. It looks like this. In 3D, what information do you get from this graph? See, for any energy starting from 0 to infinity, for all energies there is a value of density of states. You can count the states. How many states? For this energy, this is the number of states, density. For this, this is, and so on. So, it is continuous values, it is a continuum in 3D. In 3D, that means there is no restriction in the movement of the electrons or the holes, I mean the carriers. It can move freely in all the directions under zero force, I mean potential energy 0. And now come to 2D. See, this is again density of states, energy. From here up to some value, there is no state at all. There is no density of states, you see. All of a sudden, at this value of E, the density of states looks like this. This is the value of the density of, this is the energy value and this is the density of states value. So it is this, right? So at this energy, all of a sudden it jumps to a very high value. This value, this is the density of states. But below that, nothing. Now energy again increasing. See, it looks like this. That means from here to here, see, from here to here, this, for this range of energy, the density remains fixed, same. So for a range of energy, the density of states is fixed. Now when we arrive at this energy, it jumps to a high value. Density of states, from here it goes to here. Now again jumps and so on, like this. This repetition. So what information do you get? What is the difference between this graph and this graph? The energy versus density of states and energy versus density of states in 2D. Drastic change. What is that? That unless the energy of the electron reaches a particular value like this, up to this, there is no density of states. Once it reaches that value, the density of states goes to big value. It maintains that density of states, it maintains same density of states up to certain interval of energy. When it reaches energy, again it jumps, and again it keeps same value of density of states from here to here. So there is a jump of the density of states from one to the other. So this is one, say it is E1, say this is E2, next this is your E3. These are the quantum jumps, and this is the density of states. This is given dE. It is m star over pi h cross square, Heaviside unit step function E minus En, where n equal to 1, 2, 3, 4 and so on, E minus E1, E minus E2 and so on. And here the energy versus density of states, this is the e to the power half. The density of states is varying with e to the power half, some constant into e to the power half. I mean, it can take any value of e, but here the density of states is some constant, not any value. See, this is the change. Here any value of e, it can accept in 3D, but in 2D you see quantized value of the density of states. And from mathematics, the property of the Heaviside unit step function, what is that? Just if E is equal to En, then it is 1, less than En 0. So only at E1, En1, En2, En3, the value becomes 1. I mean, it steps like this, unit step function. And actually, it looks like this. remain as this. Join these points, it is this graph. So this is all about this 2D density of states. Now 1D. The 1D is it looks in 2D it looked like this in 2D. In 1D you see below this there is no density of states, but when we arrive some value, not necessarily this value, another E dash, it goes to a very high value, right? So here when it reaches to a high value in 2D, it maintains the same value of the density, but it do not maintain that. It does not maintain. See here, it gradually falls. As you move from this value higher and higher energy, the density falls. The density from here, the density of energy comes to a very low value, almost towards zero. Not zero, very, very low value. So this becomes not zero actually, it looks like this. Next one increasing, again it shoots up to a high value. Increasing, this. Again it goes like this and so on. So this is for 1D. Here the density of states is varying with e to the power minus half. Here density of states in 3D e to the power plus half. Here density of states equal to a constant, not this constant, same constant, not that, and a constant e to the power minus half. That means as energy is increasing, the density of states decreasing. So density of states is decreasing. It is totally unlike in 3D. In 3D more energy means more density of states, but here the density of states is gradually decreasing. That means packing is loose packing here. Okay. So this is one dimension. Now come over to 0 dimension. The 0 dimension, it is like this. And this is E. See, here it falls from here to here, this range of decrease of the energy, and you see the density of states are there. But here you see, once it goes to a high value like this, it goes to high value, this dotted line, it goes to this, but it falls very quickly within a narrow region like this. It's like this, it goes on like this. It is a delta function. At a particular value of energy, you can get very high value of the density of states, and then if you change from this value, no density of states. You cannot find any electron there. because there is no density of states, no states are there. So, you cannot expect any electron within, from here to here. If you shift the energy from here to a little bit value, electron cannot be there. But here you see that yes, electron may be there within this range. So, this is the characteristic feature of the 0 dimension from 1 dimension difference. Again, characterization difference from 1D to 2D and so on. So, what is important to note is that the state density is actually the packing, how close the energy levels are packed. This closeness of energy level packing in 2D, in 1D and 0D, it is drastic change from 2D to 1D, from 1D to 0D. And here in 0D means total confinement of the electron. Electron cannot move in any direction, fully restricted motion. So, the electrons will have, in the case of the 0 dimension nanomaterial, the electron will have fixed values of energies. Is it not identical with an atom? Inside an atom, the electron, say for example hydrogen atom, so positive charge and negative charge, the electron will have quantized values. It cannot go beyond the clutch of the positive charge. It is restricted to go out of the positive attraction to the negative. As if the electron is restricted to move in all the 3 directions. It is always moving surrounding the nucleus. This 0 dimension nanoparticle, is extremely small particle, say a radius, suppose say 1 nanometer, then it behaves as an atom. So, it is an artificial atom. So, 0 dimension nanomaterial, 0 dimension nanoparticle or nanoclustered, they are all like atoms. These are artificial atoms, not the natural atoms. So, very, very interesting use of this 0 dimension or 1 dimension or 2 dimension in nano science and nanotechnology, that materials are used in different applications. So, that is about the density of states. Now, the another point that I want to discuss, that is Fermi function. Now, the Fermi function, it is a function which gives us a measure of the probability. Probability of what? The probability that a particle, either electron or hole, in my semiconductor or metal, that what is the probability that a particular energy level in the material is probabilistic to hold an electron in this level. What is the probability that this electron will be placed in this energy level? Suppose I am taking, just to elaborate the idea, I am taking a sample. Now, whether 3D, 2D, 1D, 0D, anything, these have the energy levels. These are the energy levels. Energy E1, E2, E3, E4 and so on. In 3D continuous packing, I mean this difference is almost 0, continuous values. In 2D not continuous, 1D not continuous, 0D not continuous, but energy levels are there. Now, in a material, you just think that the material is filled up with so many energy levels. Now, just think that all the electrons from the material are extracted out of the material. So, this is the material and electrons are out. Now, one by one I place the electron inside. Then the electrons will take their positions, energy positions. You see, so many energies are there. Now, all the energies are vacant, suppose, but the probability that this energy level will be filled up by this electron which you throw from outside will not be the same as the probability of another energy level, this or this or this or that. The probability of this energy level to accept this electron, this probability will change. So, probability is a function of energy. I am giving this probability function as f. I should not say probability now. I tell this distribution, how the electrons are distributed. So, this is a function of energy, and also it is a function of temperature, and also it is a function of a constant quantity. This constant quantity is called Fermi energy by honor of the name Enrico Fermi. There is EF, the Fermi energy. So, Fermi, this is a Fermi function or distribution function, and this distribution function f is a function of E, then EF and temperature, and this is given by 1 over 1 plus e to the power E minus EF by kT, where E is the energy of this electron, EF is a constant energy, the value of which depends upon the material itself, to some extent also on temperature. K is the Boltzmann constant. So, this distribution function, this is the distribution function, it is a function of E at a constant EF and constant T. This is the Fermi Dirac distribution function. Both Fermi and Dirac, they just worked out on this statistics on the distribution function. So, in honor, the name is given as Fermi function. Now, if we draw the graph of this Fermi function, then it looks like this. This is Fe, this is E. Now from here to here you see that here Fe equal to 1, maximum value, because the probability can not exceed this value 1, so it's the highest value. Now from here to here, from zero energy up to a particular value of energy, the probability is fully 1, 100% probability, provided the material is at 0 degree Kelvin. Now all these conclusions I am giving you from this equation. At T equal to 0 degree Kelvin, all energies from 0 up to and equal to EF. This is EF, a particular value EF, which is by honor of again Fermi, it's a Fermi energy. Up to this highest value, from 0 to this, all energy levels are occupied with 100% probability. Probability is 1. So for this E, yes, Fe1. For this E, Fe1. That means that if you take 0 degree Kelvin this specimen, then suppose there are so many levels, up to this level, say this is EF, I give the name, the highest level up to which they must be engaged with electrons. They are accepting the electrons with 100% probability, but after that no question, the highest value of the energy, and this is your Fermi energy or the Fermi level. So Fermi level is defined as, if a material is at 0 degree Kelvin, then what is the highest value of energy which is occupied by electrons? Yes, up to this. Below, yes, occupied, and after that no occupation. But if it is not 0 degree Kelvin, come to a finite temperature, so room temperature, then you will see that it looks like this. What is the difference? At Fermi, which we defined in the 0 degree Kelvin like this, 100% chance, at Fermi the chance comes down, this is the chance, and this is half, Fe equal to half. This is F equal to 1, just middle. So at Fermi level, the occupation chance, the probability, occupation means the probability that the electron will occupy this energy level EF, that is the occupation chance. So if I ask the question, what is the occupation probability for say copper, for say germanium, silicon, anything at a finite temperature, at a Fermi level EF, 50%. So 50% chance that the electron will occupy the energy level value EF. C, the difference. Here, above EF, still there is a chance. You see, above EF this value, there is a chance. Above this value, there is a chance. Of course, the chance is coming down and down, but there is a chance. But if the material is at 0 degree Kelvin, no chance at all, no electron above EF, all electrons below EF. So, this is a good observation that if the specimen is at a finite temperature other than 0 degree Kelvin, there is a chance that some electrons may occupy above the value of Fermi, but with lesser probability, less than half. So, this is about the Fermi function. And also you see that if it is below EF, I mean the energy is below, lower than the Fermi, then you see that the probability increases. So, with lower energy, the electrons will have, the lower energy level will have better option to accept electrons. Yes, from here the probability is higher. So, that is the conclusion of this Fermi function. Yes. Now, let me pass over to the another point, which is the dispersion relation. The dispersion relation, it is a relation between the energy of a carrier with its corresponding momentum. Momentum they measured by h cross k. So, it is E versus k. This relation is known as the dispersion relation of the carrier. So, inside the semiconductor or any material, the electrons, they are the carriers of electricity, holes, they are also the carriers of electricity, and they are arranged in energy levels. How they are distributed, that we have already talked about all these things, and they have some momentum h cross k. How these E and K are related? Now, in 3D, it is E equal to h cross square by 2 m star k square, where k is kx square plus ky square plus kz square. So, if we draw the graph, it looks like this. This is k with vector energy. It is the momentum, actually h cross k, the momentum. So, E versus k is this. It is a parabolic relation, you see, it is a parabolic relation, constant multiplied by k square, and for k is plus or minus, same energy. Right. K plus minus means the electron may go in this direction if it is a plus, and it comes opposite minus k. So, it is E versus k is this, where k is actually kx square plus ky square plus kz square. It can take any value of k in 3 dimension. It is a continuous value. Now, 2D. In 2D, the energy is equal to h cross square over 2 m star kx square 2D. So, one dimension is restricted. So, it is this. Z direction is restricted. So energy versus K, this is the relation. Now from here you see, when K equal to 0, energy is 0. It's a bulk material. Now if we take a plane material, only x and y, z direction is restricted like this, then when kx, ky, this is kx, suppose this is say ky, that means suppose this is your motion direction, it is your kt, then kt square equal to kx square plus ky square. I am just giving this as kt square, transverse wave vector, kt square. So h cross square by 2m star kt square, where kt square equal to kx square ky square plus h cross square 2m star over n pi over L whole square. L is the nano dimension in the z direction, n equal to 1, 2, 3, 4 and so on. Now notice that even if kt equal to 0, there is energy, because it is not 0, it is never 0, because the minimum value of n is not 0, 1. So h cross square 2m star 1 pi by L whole square plus 0. So this is the potential energy is there. So if I draw the graph, then if this is the kt, then for kt equal to 0, still there is energy this. For kt equal to 0, there is some energy, this value. This energy is equal to h cos square 2m star n pi by L whole square. Now from this energy n equal to 1, now go on increasing kt, then it looks like parabola. Yes. So it does not start from 0 like this in 3 dimension, it starts from a higher value, right. Now for the holes, you see here also, if you draw the graph of holes, then the hole looks like this. This is a graph. So sorry, this is a conduction band and this is the valence band, not the holes. Conduction band and this is the valence band, right. Now here the valence band also likewise it will come down. So effectively you will see that the band gap is this, increases. The band gap increases in this case. If you take 1D, it is h cross square 2m star, then kx square plus h cross square 2m star, it is n1 pi by L1 whole square plus h cross square 2m star n2 pi by L2 whole square. Why? Because here in 1 dimension only 1 dimension is free, kx, both ky is quantized and kz is quantized. So see, even if kx equal to 0, still there is some energy, where n1 equal to 1 to so on, n2 is also 1 to so on, quantum numbers, and therefore the graph looks like this. This is your kx, this is E, and this value is energy with N1 and N2. It goes up. Similarly here also in the valence band. So band gap increases in comparison with the 3 dimension. So in 2D the band gap increases, right, from the conduction band valence band distance this. So these are the dispersion relations, and in 0D E equal to, all these are quantized, that means H cross square 2m star, it is N3 pi by L3 whole square plus H cross square 2m star N1 pi over L1 square plus H cross square 2m star into N2 pi over L2 whole square. All these are quantized. So these are the dispersion relations for 0D, 1D and 2D for the nanomaterials. So these are essential in order to study the transport in nanomaterials. When we shall go over to these graphene, these basic things are needed there, and finally we shall pass over to the carrier concentration. The carrier concentration, say in the suppose I am taking a semiconductor, then the carriers are in the conduction band, then this is, I am taking, suppose this is conduction band and this is the valence band and electrons are here. How many electrons are there in the conduction band? The expression to determine the electron concentration is this: if n is the electron concentration, what I mean by the concentration? Number of electrons per unit volume, that is it, electron density. So electron density, how many electrons in unit volume of the semiconductor? This is equal to dE Fe dE with integration from 0 to infinity, where d is the density of states at energy E, Fe is the probability, occupation probability of energy E for occupation of an electron, and dE is infinitesimal, and this is the integration. Now to explain, let me explain this mathematics. See, dE is the number of electrons per unit volume, right? Number of electrons per unit volume. So electron density comes per unit volume. So number of electrons per unit volume, but per unit energy distance. But inside the semiconductor, why I should take only unit difference from here to, as long as the electron levels are there. So I am taking from 0 to infinity. There is a cutoff point. No matter, it will not hamper the mathematics. So after the cutoff point, all will be 0. So I am taking 0 to infinity, indefinite integral. Number of electrons within this span from 0 to infinity, number of electrons within total this energy dE running from 0 to infinity. dE, this E runs from 0 to infinity. So I am covering all the energy levels with this dE integration, and dE is the number of states. Now each state, suppose there is only one state or two states, then if there are two states, are you sure that these two states are filled up by electrons? No, there is a chance, there is a probability. If 30% chance may be there, it is not 100%. So we must multiply by a probability function, because if it is 100, not 100 electrons are there, because some levels may be vacant. So, you multiply by the probability function. So, this is the justification of this mathematical formulation that n equal to 0 to infinity d f d, this gives the electron concentration or the carrier concentration. In the case of holes, density of holes multiplied by the probability of the holes at energy E, and it goes to 0 to infinity, and this is your hole concentration, not n but P, the hole concentration. So, these are the some of the basics to enter into the subject of graphene, which I will talk later on, and these are the preliminaries. I have tried a little bit to give some idea on the necessary quantum mechanics, what I mean by the nanoscience, nanotechnology, what I mean by dispersion relation and density of states function, all these things which are related to study any nanomaterial in nanoscience and nanotechnology. Thank you very much.